today what we are going to do is actually understand what the primal simplex method does to the dual dictionary without actually looking at the primal dictionary. In other words, the previous lecture we had the green and red dictionaries. One was a primal, the other was a dual. Looking at the primal simplex method applied to the primal problem. And we just constructed the complementary dictionary by looking at the negative transpose of the primal dictionary. So today we are just going to redo the whole thing without actually looking at the primal dictionary. So this is a method that's going to work with infeasible dictionaries to satisfy optimality conditions and work its way towards achieving feasibility. That's called the dual simplex method. Then I'm going to tell you more on the matrix notation that we started 2 lectures ago. I briefly told you what that looks like. So we do a very quick overview of matrix notation and how the simplex method works, what dictionaries look like in terms of matrices, and then we get started with sensitivity analysis, and this will be finished in the next lecture on Thursday. So that's going to wrap up roughly the first third of the class in terms of topics, although more lectures than just in terms of the course. Now, I did hear from a lot of you about the midterm, and so we will have the midterm on the 27th or the 25th. 25th is a Tuesday, I guess. So, of the 2 days, if there's any one that's better, let me know. Yes? What's the exam that... okay.
But it's not the same hour.
Of course, yeah. So, yeah, we could have it on the 25th. If all of you agree to have it on the 25th, then we could have it on the 25th. Okay, so 25th in class. Now the difficulty is, I know you have a class soon after. Yes.
Oh, right.
10:30. Right? So that means that all of you should be here on time, and we finish exactly at 10:30 because somebody has to leave. Otherwise, well, the other possibility is that you go to your class a little late, and then, if necessary, we can have a little extra time. This is the only reason.
I'm sure that exam got that time.
Actually, if we finish exactly at 10:30, you'll have lots of friends, of course. Okay, so the exam will be on the 25th. It'll be 9 to 10:30. Please be here on time. And with the understanding that I may extend, give you 15 extra minutes or so. I mean, there's a class here at 11, so we have to finish by then. But, it's going to be an exam meant to be done in an hour. As promised, I will post a sample midterm exam with solutions, and you'll get enough practice. So, Okay. And if calculator is allowed, nowadays you can do lots of things with your hand calculator, including have a version of Excel, do lots of these things. So don't do that. If you're asked to actually show your work and solve a problem using a certain method, you will not get any credit for just having the final answer. Because you get a lot of credit for having a wrong answer as long as your method is reasonable and your errors are because of calculation errors and so on. So in particular, even though I say calculators are allowed, I don't think you will need to use one. Similarly, even though it's open book and open notes, you probably will not need any of these. Because typically, if you keep looking up your textbook and notes, you run out of time. Okay? So this is just to take pressure off of you, in the sense that you shouldn't feel that you have to remember lots of little things. Okay? But the exam will test your understanding. So as long as you understand the methods and why they work, it should be easy enough. Any questions about this? Okay, so let's go on. So here's a linear programming problem. Maximize minus 5y1 minus 35y2 minus 20y3, subject to a couple of constraints and non-negativity restrictions. And notice that this particular problem is written in standard form, the way we understand it, right? It has equality constraints, has a maximization objective, non-negativity restrictions on the variables. And so you can write down the obvious initial dictionary, which is what's written here. So you have the W's as slacks, and W1 is this, W2 is this, and Z is this. Okay? So this is a valid dictionary. Y1, Y2, Y3 are all non-basic variables, and the two variables in your problem are expressed in terms of the non-basic variables. The objective function is expressed in terms of the non-basic variables. Okay. So this is a valid dictionary. The only problem is it's infeasible. Okay. It's infeasible because the natural solution we associate with this dictionary is all the y is set to 0, and therefore W1 is -2 and W2 is -3. Okay. So if I give you such a problem and you attempt to solve it, what would you have to do? So how would you solve this linear program? Anybody? By applying phase 1. Very good. So you would have to add 2 artificial variables. So if you were to solve this problem using the primal simplex method, the method that we know and understand, then first you have to find a feasible dictionary. Right? At this point, it's not even clear that there is a feasible solution. So first you would add A1 and A2, which are artificial variables, and you will set up the phase 1 problem of minimizing A1 plus A2, subject to these 2 constraints, with A1 and A2 added. Once you finish phase 1, at the end, this, as it turns out, has a feasible solution. And therefore, you would end up with a dictionary in which both A1 and A2 are 0. And so you would then be ready to set up phase 2, where you will introduce this objective function. You will continue. Now, what we are going to do instead is to use what's called the dual simplex method. So this is going to avoid dealing with or avoid doing phase 1, but what it's going to exploit is the fact that these coefficients are all negative. And therefore, we are well on our way to satisfying the optimality conditions. Okay. So the point is, if the solution were feasible, then we wouldn't have to do any work. This would be an optimal solution. So the difficulty is that this is infeasible. So you should also keep in mind, therefore, that the objective value of the current solution, which is 0, is perhaps not achievable. That the optimal value is going to be smaller, right? Because you have an infeasible solution satisfying the optimality conditions. So if this were feasible, you would stop, and this is an optimal solution with value 0. The fact that this is infeasible, but optimality conditions are satisfied, means that as you move towards feasibility, you're going to decrease this objective function. Okay? So you can apply this method that we're about to discuss as long as the optimality conditions are satisfied, meaning as long as the coefficients here are all negative. And what we are going to do is go through a sequence of iterations where these coefficients, the -5, -35, -20, all of those will remain negative. They won't be the same, obviously, but they'll remain negative or remain non-positive. And we are going to slowly work our way to achieving a feasible solution. So in the primal simplex method, our goal was to start with a feasible dictionary which is suboptimal. There are certain coefficients in the last row with positives that are positive. And we are going to introduce some such variable into the basis, and some other variable is going to leave. And the condition is that you'll always maintain feasibility. That the first column will always be non-negative. So here, the condition for determining which variable enters the basis is going to be that this coefficient, the coefficient of the last row, will always be non-positive. Okay, so this is the idea, and you can apply this method anytime optimality conditions are satisfied in a dictionary. So whenever you have a dictionary where the last row has negative coefficients or non-positive coefficients, you can always apply the dual simplex method. Of course, if these two things here, if instead of being -2 and -3, if they were +2 and +3, you would just stop. Because you have a feasible solution satisfying optimality conditions, this is the best possible. So, what is pivoting in this case? Well, we are going to first decide what our leading variable is. So this is in contrast to the final simplex method where you first decide what your entering variable is. So we can, in general, we are allowed to pick any variable that is negative value as the leading variable. So, you could suggest, and a common rule is to pick a variable with the most negative value, but it doesn't have to be that. So here, for instance, if you pick W2 because it's the most negative, then that's going to be your leading variable. Now, to decide what the entering variable is, you want to look at, so the fact that W2 is a leading variable means that this is going to be the pivot row. Of course, once you decide what the entering variable is, then you will have the pivot element, which is the element that's going to become basic, and you will do the operations the usual way. So for instance, if I tell you that Y1 should enter the basis, then how would you go about it? Well, now it doesn't matter, right? So we have this dictionary, Y1 enters and W2 leaves. We know how to do this, right? So we would start with a pivot row, express Y1 in terms of the new non-basic variables, which are W2 and Y2. Okay. So given this, you would say Y1 equals 3 minus 3Y2 plus W2. Right? And so this is going to be your new second row. Moreover, wherever Y1 appears in the dictionary, in other places, you would use this expression. Okay? So it's the exact same operation. So use this expression for Y1 everywhere else in the dictionary. Now, how do we figure out that Y1 is the entering variable? So just like we do a minimum ratio test to determine the leading variables in the primal simplex method, we will do a minimum ratio test to determine the entering variables in the dual simplex method. Okay, so you should see the symmetry. And the way you would determine that is, of course, to look at the ratio of the coefficient of any variable in the last row to its coefficient in the pivot row. Now, if you observe that the coefficient in the last row by definition is always going to be non-positive. So you look at the negative of that quantity. So I have a minus 5, so I'm going to do 5 divided by 1. Similarly, for Y2, it's going to be 35 divided by 3. For Y3, it's actually going to be 20 divided by 0. But 20 divided by 0 is infinite, and it's not going to achieve the minimum ratio, so we don't even write it down. Okay. As before, the only variables that will participate are those that have positive coefficients in the pivot row. So in this case, both Y1 and Y2 have positive coefficients, so both of them participate. Okay. So you'll see later why that's the case. So we compute the minimum ratio, where we take the absolute value of the coefficient of any variable in the last row, divided by its coefficient in the pivot row, as long as the coefficient is positive. If it is 0, you're going to achieve an infinite ratio anyway, so it doesn't matter. And if it is negative, you just don't use it. The reason is, if something has a negative coefficient, it's actually easy to see that when you do the operations and write down the correct Z finally, you will end up with a positive coefficient in the last row. That you don't want. You will violate the optimality conditions. So if you pick anything else other than the minimum, you will violate the optimality conditions. And those that appear with a negative coefficient pose no danger to your violating the optimality conditions. So they don't determine anything. Just as in the primal simplex method, only certain variables participated in the minimum ratio test. If some variable had a positive coefficient, it didn't participate in the minimum ratio test because you were in no danger of violating feasibility. Exactly the same argument in its symmetric form. Okay, any questions about this rule? Okay, so I'm going to use this value of Y1, and I'm going to express my new dictionary. So as you can see, Y1 is exactly the expression that I wrote down. The W1 and the Z1 now have their Y1s replaced by this expression, so that everything is now in terms of Y2, Y3, and W2. Okay? And this is the new dictionary that you get. You've made some progress, so Y1 is now positive. Okay. Observe that all the coefficients in the last row are negative still. So none of them became positive, and that's the key. So your pivot operation is designed to ensure that you never make any of the coefficients in the last row positive. Observe also that the current solution has lower value than what we started with. So before we had a solution with value 0, and infeasible solution with value 0 satisfying optimality conditions. Now we have still an infeasible solution with value negative 15. Okay. Everyone comfortable with this? So now what happens? Well, for the leading variable, you have no choice. There's exactly one variable with a negative value, W1. So that leads. And to determine what enters, you want to look at the ratios. Okay? And as I said, so this is going to be the pivot row. And as I said, to do the ratios, you look at the absolute value of the coefficients. So for y2, it's going to be 20 divided by its coefficient in the pivot row as long as it's positive. Okay? So it's 20 divided by 4. Similarly, for y3, it's going to be 20 divided by 1. And W2 is not going to participate. Because it has a negative coefficient there. So therefore, from this dictionary, if you do a dual simplex pivot, W1 leaves and Y2 enters. Okay? W1 leaves and Y2 enters. Is that clear to everyone? Please stop me if there are any questions. Okay, so once again, you're going to use the pivot row, express Y2 in terms of W1, Y3, and W2, and that's easy. So you'll have 4 Y2 equals 5 minus Y3 plus W1 plus W2. Which means Y2 is going to be this quantity divided by 4. So Y2 is 5 over 4. And you would continue. So this is just taking this expression for Y2, substituting it in the other two equations so that now you have everything in terms of a new set of non-basic variables. Now, what happens if you have a row? So what happens, actually maybe I have it in the next slide. Okay, so that's your new dictionary. You can look at it. Now notice that in the new dictionary you still have infeasibility. So in the previous solution, y1 was positive, y2 was not. Now you did a pivot, y2 became positive, but y1 became negative. Okay, so there's no guarantee that once something becomes positive, it will stay positive. Of course, the other observation is the last row, the coefficients still stay negative, and your solution has even less value than what you had. So here, of course, y1 has to leave the basis, and when y1 leaves, w1, which is here, has a negative coefficient. It's not going to participate in the minimum ratio test. y3 and w2 do, and you can check that y3 enters. Okay? Yes?
Is it possible for a leading basic to become a basic again? I'm not talking about a particular example, just curious whether...
Is it possible for a variable that...
a leading variable to become a basic variable again after some kind of iteration?
Yes, it is possible. This example doesn't have such a property.
Okay.
Maybe it doesn't, but yeah.
Because a friend asked me that question, I said yes, and the one
it is possible. So you can construct examples where a basic variable leaves the basis and then enters the basis again. Yeah. In fact, so you can easily see that if that were not true, you would have only a small number of iterations. to solve the linear programming problem. Because in every iteration, there's a new variable that became basic, so you can't have more than linearly many iterations. Okay, so Y3 enters, Y1 leaves, and one can actually work out the details. The next dictionary will turn out to be optimal. But what happens if this is true? So what if you have a row where, I think people can't see this very well. Let me, can everybody read that, what is written in light green? Okay. So what happens if y1 is -3 minus 3y3 minus w1 minus w2? Suppose that's your pivot row. Well, so you will still determine that y1 leaves, okay? What enters the basis? So to decide which variable enters the basis, you would do the minimum ratio test, except that all of these variables have negative coefficients. So none of the variables participate in the minimum ratio test. Okay, so the suggestion is that perhaps the problem is infeasible. Why?
There's no further steps to take.
There's no further step to take. Okay, so that's a very good answer. So notice that all along you work with dictionaries that satisfy optimality conditions, and suddenly you have nowhere else to go. You can't make any further steps. So perhaps the problem is infeasible. How do you see that? Well, remember that all the variables are non-negative, right? So in particular, y3 is non-negative, w1 is non-negative, and w2 is non-negative. And you have y1 equals -3 minus something, minus something, minus something. Each of those quantities is a positive quantity. So y1 has to be negative, right, in any solution. So how can you ever have a positive value for y1? It's just not possible. In other words, if you look at this equation in a different way, so this equation just says y1 plus 3y3 plus w1 plus w2 equals -3. That's exactly what this says. And all of the variables are non-negative. This is not possible. Okay? So, if you run into a case where there's a pivot row and every variable has a negative coefficient or a non-positive coefficient, then the problem is infeasible. Observe that in the primal simplex method, if none of the variables participate in the minimum ratio test, the problem is unbounded. You can increase, so you figure out some variable with a positive coefficient enters the basis and nothing leaves. That means you can increase the value of the variable to as high a value as you like, and you will stay feasible. So your problem is unbounded. Here, if the minimum ratio test can't be done, the problem is infeasible. This should not be surprising, because we already saw that if the primal problem is unbounded, the dual problem has to be infeasible. Right? This was the result that we proved last time. And so, if you view this method as what the primal simplex method does on the dual dictionary, that's our point of view, then it shouldn't be surprising that you get such a conclusion. Okay? Okay, so if you take this even further, so one more step, you end up with something like this. Okay? So that the green dictionary there is what happens after you do the pivot suggested in the previous line. Yes.
Just want to ask a question about the private example.
Mm-hmm.
When we saw that it was infeasible,
Mm-hmm.
we had to do all these steps to see that, or we can get aware of this right away when we see the problem?
No. So remember that, okay, so in this case, it's only at this stage that you will discover the problem is infeasible. Now, like I said, you can represent linear programs in many different ways. In particular, every dictionary is a representation of a linear program. There are certain representations where it's obvious to, the optimal solution is obvious. There are certain representations where it's not. Similarly, there are certain representations where feasibility or infeasibility is obvious, and certain representations where it's not. So, in this particular problem, suppose it were infeasible. Here, in fact, it is not. Suppose I give you an infeasible problem. You may be able to write down the first dictionary that satisfies the optimality conditions. It's infeasible. But of course, you have no way of knowing that the problem is infeasible. All you know is that the particular solution that you're starting with is infeasible. And you're searching for, you're trying to find a feasible solution. At some point, you fail. And the failure will always look like what is here, written on the slide. There will be some row which looks exactly like that, and then you will conclude that the problem is infeasible. So the point is that if I give you an infeasible linear program, it's not easy to tell that the problem is infeasible. You still have to work to verify that for yourself. Okay. Any other questions? So again, just to reiterate my point, if I give you a linear program with the following objective function, okay, so let me write it down here. So I want to maximize minus 20y1 minus 20w1 minus 5w2 subject to y2 plus 1/3 y1 minus 1/3 w2 1 y3 minus 4/3 y1 minus w1 1/3 w2 with 1 y1 y2 y3 w2. If I gave you this linear program, I claim that this is trivial to solve. Why is that? Well, I look at this. I have y1, w1, and w2 all with negative coefficients. Okay? And they all have to be non-negative. So the best I can do is set them all to 0. Because if I set any of them to any positive quantity, I'm going to incur a cost. Right? They all have negative coefficients. So my natural strategy would be to say, try y1 is 0, w1 is 0, w2 is 0. If this gives me a feasible solution, if I'm able to extend this to a feasible solution, that has to be optimal. Okay? Because this is the only way for me to achieve value 0. Any other value for any of these quantities is going to give me a negative objective. So I set these, and then I find, okay, so y1 is 0, w2 is 0, so y2 has to be 1, and y3 has to be 1. So notice that this implies these two things. Okay. This is feasible, and therefore it's so optimal. Okay? Now, instead, what I did give you was a different problem. So what I gave you was this problem. This is the problem that I actually gave you, and here the same trick does not work. In fact, the fact that your first dictionary is infeasible is precisely because the same trick doesn't work. If you set y1, y2, and y3 all to be 0, you get w1 to be negative and w2 to be negative. That's not feasible. Okay. Now, the whole point of the method that we discussed is that we start with this problem through a sequence of other problems, which we call as dictionaries. We end up with this problem, where figuring out what the optimal solution is trivial. Now, in going from one step to the next, we always preserve solutions. So any solution to the first problem is a solution to the second problem. Any solution to the second is a solution to the first. Okay? And they have the same cost. So because we go through this transformation, always maintaining not just a set of feasible solutions, but the cost of every solution. One view of the simplex method is just a way of transforming the given problem into another representation, so that figuring out what the optimal solution is a trivial task. So so when you conclude infeasibility, this is the way I'd like you to think about it. This problem, as given, it's not easy to see that it is infeasible. But as you go along, changing your representation, some representation makes it very easy for you to see that the problem is infeasible. Just as this representation makes it easy for you to see that this solution is optimal. Notice that this solution is optimal for that problem as well, because these two are equivalent. The fact that this is optimal for that problem is not as easy to see as the fact that this is optimal for this problem. And we infer that what we find is optimal for the problem we started with, because every iteration in the sequence of iterations that we do preserves solutions. And so anything that's optimal for this problem is optimal for that problem, and vice versa. Okay? I mean, it's a very simple point, but it's worth understanding. Yeah.
What if we start with some coefficients that are positive?
What if you start with some coefficients that are positive? Well, you could, right? I mean, this is, in the primal simplex method, this is what we would do. We start with some positive coefficients, but then somehow transform them into a system where you can apply such an argument.
So, like, I'm just wondering which way would be more work for us doing, like convert it like as a regular treat as a regular primal thing, or we convert it to like.
Okay, I see. So I think the question is, when do you apply the primal simplex method? When do you apply the dual simplex method? And what if neither one can be applied? Now, when do you apply the primal simplex method? Well, if the problem that you're given is such that the natural dictionary associated with it is feasible but does not satisfy optimality conditions, you apply the primal simplex method. If, like in this problem, the natural dictionary associated is infeasible but satisfies the optimality conditions, you apply the dual simplex method. Of course, it's very easy to construct problems where neither one is true. For instance, I could make this, if instead of this, I have 5 y1 plus 35 y2 minus 20 y3, then it's not clear what method you apply. Okay? Because here, if you write down the dictionary, the last row is going to have positive coefficients, so it doesn't satisfy the optimality conditions. And the natural dictionary is going to be infeasible, because it's going to be the first two rows of the dictionary is going to be the same as what we did. The last row is going to change, and it's going to have some positive coefficients. So neither the primal simplex method nor the dual simplex method can be applied. Okay? And then what do? You have to do phase one. You could do phase one for you could do the usual phase one, right? You could introduce artificial variables, try to minimize, and so on. So the point of all this is not that the dual simplex method is always applicable when the primal simplex method is not. The point is that there are enough situations where having something like a dual simplex method is useful, and you'll see some of that when we discuss sensitivity analysis. The other point is that there are situations where you cannot apply the primal simplex method, but you don't have to go through this two-phase method if it happens to be a problem like the one we started with.
Can you explain again, I'm sorry, how it's not applicable to either?
This is not applicable to either because if you look at the dictionary, so let me write down the dictionary for this. If that's the objective function and these are the constraints, my dictionary is going to be W1. So that's my first row. This is my second row. Right? So, to apply the primal simplex method, I want these quantities to be non-negative. So I want these to be non-negative to apply the primal simplex method. To apply the dual simplex method, I want these to be non-positive. If either one of them is true, we can apply the appropriate method. Here, neither one is true. So this, here I don't have positive coefficients. I have negative numbers. And here, I don't have all negative coefficients. Some of them are positive, some of them are negative. So I can't apply the dual simplex method, I can't apply the primal simplex method. Of course, when I say I can't apply the way we have studied it. Maybe there are other versions that might work with such a thing, but that's not of interest to us. So is that clear to everybody? I want to show you one other thing. This is the optimal dictionary. Okay? The dictionary in green is the optimal dictionary for the problem that we solved in this lecture. If you go back to an early lecture where we studied the simplex method, we looked at the following problem. Maximize 2x1 plus 3x2, subject to those three constraints, and we said the optimal solution is this. Okay? So that's the optimal dictionary for that problem. And I just want you to observe that the problem here in red is just a dual of the problem that I wrote down in class. It's just the dual of the problem we started with, the green problem. And the red dictionary, the optimal dictionary, that I didn't compute for you today, but that we did a couple of weeks ago in lecture, this satisfies the negative transpose property. So this dictionary is exactly the negative transpose of the green dictionary. So how do you get that? Well, associate with any y the corresponding s. Okay, so y1 goes with s1, y2 with s2, and y3 with s3. And x1 with w1 and x2 with w2. Okay. So these are the complementary variables, right? The variables, regular variable in one problem with the slack in the other. The x1 row is going to be the same as the W1 column. Okay. So the x1 row has 20 as a constant, has a -1 for S2, a -1 for S3. If you look at the W1 column, I'm sorry, so I said something that's incorrect. So if you look at the x1 row, so x1 is 20. Okay? So x1 is a basic variable, its value is 20. Now by complementary slackness, what do you know about the W? W1 has to be 0. Therefore, W1 must be a non-basic variable. Okay? Thinking something is not right. I think there's some error in one of these dictionaries.
For the x1 row, Monday and one, there is no like W1 and Y2.
So let's see. So if you look at the S3 column, so S3 has -1, 1/3, -4/3. So Y3 should have +1, 4/3, 1/3, and 1. That seems okay. Look at the S2 column. Has -1, so Y2 has a 1. -1/3, 1/3, -1/3, -1. So you should have -1/3, 1/3, and 1. So I think there's some term missing in the first row of the dictionary. Just give me a moment to check this with your textbook. Okay, so I'm pretty sure that Y2 row is incorrect. Rather than do this in class and waste time, why don't we just check it offline, and I'll fix it in the notes before I post it. Okay? So what must be true is that if you do the natural association, okay, so the Y's go with the S's, the X's go with the W's, and then take the negative transpose of that dictionary, you should get this dictionary, and vice versa. And the one example that I said the first time didn't work, and that's the problematic one. So let me fix that and then I will post it. So, so I guess what I wanted you to observe here that's not apparent is the fact that if you know this dictionary, then you can construct that dictionary without doing any computation, and vice versa. Okay? And of course, observe that the last row of the red dictionary has the optimal dual solution, which is 1 and 1. And the last row of the green dictionary has the optimal primal solution, which is 20, 20, and 5. Okay? And that should not be a surprise. Okay? So we are going to actually use this property in writing down a proof that the last row of the primal dictionary, which is given here, gives you the optimal dual solution. So I'm going to show that to you in a little while today. Okay. So this is the dual simplex method. As I said, for this particular symmetric form linear programs where you have maximized C transpose X, AX less than equal to B, X non-negative. That form, you can think of the dual simplex method as a primal simplex method operating on the dual. That's the way we discuss everything. We already saw in class, and you have a little homework problem that says that such a form is general, that any linear programming problem can be converted to that form. You can also develop this method for other forms. That's not too difficult, and we're not going to do that explicitly. It's the exact same thing. In the remaining 20 minutes or so that we have, what I'd like to do is discuss a little bit of this matrix notation, and also convince you that the strong duality theorem is true. So give you a proof of the strong duality theorem. Okay? So let me just keep that linear programming problem there, and probably use the board to do this. So I want in fact, let me work with this problem. So we are going to work with this red linear program, which has 3 constraints, 2 variables. We've solved it in many different ways. Let's actually represent it in matrix terms. Okay? So the x vector is going to be x1, x2, s1, s2. So I'm looking at the standard form version of that process. So the C vector is going to be 2, 3, 0, 0, 0. So this is the coefficient of the corresponding x in the objective function. So x1 has a coefficient of 2, x2 has a coefficient of 3, s1 has a coefficient of 0, s2 0, and s3 0. So a constraint matrix, the A matrix, is given by the coefficients of the corresponding variables in each of the constraints. So we have 3 constraints and 5 variables. So this is going to be a 3 by 5 matrix. Okay. The coefficients in the first row are -1, 1, 1, 0, 0. For the second row, it's going to be 1, 3, 0, 1, 0. And for the third, it's going to be 1, 0, 0, 0, 1. Does everyone understand where this comes from? this is the x1 column. So x1's coefficients in the 3 rows are -1, 1, and 1. Right? Because x1 appears with a negative sign in the first constraint, the +1 coefficient in the second, and +1 coefficient in the third. Similarly, x2. So let me write this down. This is x1, x2, s1, s2, s3. Okay. So the slacks obviously appear in exactly one constraint. So S1 appears in the first, S2 in the second, and S3 in the third. So with this notation, and of course your B vector is going to be 5, 35, and 20. So with this notation, the linear programming problem is just maximize C transpose X subject to AX equal to B X non-negative. And you can check that. Okay? Now, what does a dictionary look like? Okay. So to figure out what a dictionary looks like, we have to first decide what basic variables are and what the non-basic variables are. So for instance, if you look at this optimal dictionary, what is your set of basic variables? It's x1, x2, and s1. Okay. So I could actually represent, so let's actually work with this set of constraints. But let's separate the A matrix into the columns corresponding to the basic variables and columns corresponding to the non-basic variables. So I'm going to let A be partitioned into B and N. Okay? So these are the columns of basic variables. And these are the columns of non-basic variables. Okay. Now, here it so happens that x1, x2, s1, these are the basic variables, so they're all lined up. Okay. But they don't have to be. It could be x1, s1, and s2. So in which case, B matrix will be this, this, and this. So in our particular case, B is given by -1, 1, 1, 1, 3, 0, 1, 0, 0. Okay. N is given by 0, 1, 0, 0, 0, 1. Okay. Does everyone understand this notation? So your A matrix is just these 3 columns next to these 2 columns. Of course, if you have to reorder, so let me write down, suppose the basis is x1, s1, and s3. Okay. Then the B matrix is going to be -1, 1, 1, 1, 0, 0, 0, 0, 1. Okay? Your N is going to be 1, 3, 0, and 0, 1, 0. But it's important to keep in mind what these columns are. So this is the x1 column, this is the s1 column, and s3 column, x2, and s2. So once I know what the basis matrix is, I could rewrite instead of A, X equals B, this is the same as saying B, N, so that's the A matrix. But notice that I may have rearranged my columns. And so when I write x, I want to rewrite it as xb, xn. So this is the column vector of all the basic variables. This is the column vector of the non-basic variables. So in this particular case, xb is going to be x1, s1, s3. And then it's going to be x2 and s2. So the same way you arrange the columns, you have to arrange the variable names. So this is the same as saying okay. And now we know how to multiply these. So this is the same as saying b times xb plus n times xn equals b. So those are your constraints. So this is just a different way of writing the equations. It's the same set of equations, ax equal to b. So you still have 3 equations and 5 unknowns. But this is just a different representation that's going to be useful in a little bit. Okay. So let's actually take that. Let me erase this and let me show you. So my linear programming problem was maximize C transpose X, AX equal to B, X non-negative. That's the same as saying maximize CB XB plus CN XN. Okay. Just separating the cost coefficients as well into the basic and non-basic components, subject to B times xb plus n times xn equals b. Now, I'm sort of now thinking about this problem not as an LP, but as the following. Suppose we are given a B. So suppose I give you a basis matrix, or suppose I give you the set of basic variables. What do you do with it? Okay, how do you get this dictionary representation, for instance? So we know how to do this, right? If I tell you use x1, x2, and s1 as the basic variables, then you will rewrite every equation such that each row has a unique basic variable that appears nowhere else. Okay, so this is what we want. That's the same as saying the following, that I want the top of my dictionary, everything except the last row, to involve just the basic variable. So I want everything in terms of basic variable equals everything in terms of the non-basic variables, right? This is the representation that we're looking for. Therefore, I could I could take this constraint, multiply it throughout by B inverse. So B inverse times which is B inverse times B is just the identity. So you get XB plus B inverse N N. Okay. Now, lots of questions should occur to you. First of all, why should B have an inverse? Not every matrix has an inverse, right? Which matrices can be inverted?
Linearly independent.
So the rows have to be linearly independent, or the columns have to be linearly independent, which are the same thing. But more importantly, it should be a square matrix. These if you talk about regular inverses, there are other kinds of inverses that apply more generally. But the matrix inverse that we are familiar with applies only to square matrices. Are you guaranteed that B is a square matrix? Was it, I erased, unfortunately, my example, but is it a square matrix here? Yes, it is. In general, will it be a square matrix?
Yes.
Yeah. Yes, right? Because you're going to have as many basic variables as the number of constraints. So this is the reason why if you have 3 equations, you pick 3 basic variables. Okay? Now, why does it have to be invertible? We didn't actually discuss it, but only those set of basic variables that give rise to a unique solution, regardless of what values you fix for the non-basic variables, only those are valid sets of basic variables. So in fact, by definition, a set of variables form a basis if and only if the corresponding B matrix is invertible. So this exists by definition. That's just a fancier way of saying that if you pick a set of variables as your basic variables, suppose the corresponding B matrix cannot be inverted because there's some linear dependence between the rows or the columns, then that is not a valid choice of basic variables. Okay. So that takes care of that problem. But this is almost what we want, right? So this says, remember that this is just numbers. N is just numbers, right? These are, if I tell you what the basic variables are, these are just numbers. B inverse exists, so we can actually multiply all of this. And therefore, this is the representation that I want. XB is B inverse B minus B inverse N XX. For any given choice of B matrix, if you compute this quantity and explicitly write out this set of equations, you would get the entire dictionary except for the last row. Okay? So if I give you the B matrix, the only thing you need to do is invert it and then do this computation to find the associated dictionary. So all the steps that we did in going from one iteration to the next and so on can be regarded as a way of doing this computation implicitly. Okay? Let me actually show this to you on let's look at this dictionary. Okay. So we want Y1. So I'm going to now write down an example, and I want to show you that that dictionary can be designed. So I want Y1, Y2 basic, Y3 W1, W2 non-basic. Okay. Yes.
Can you use another color, please?
Was green okay, or?
Yeah.
Okay. So this is going to take about 5 minutes. We do this computation and then we pick up things in the next lecture. So Y1 and Y2 are basic. Y3, W1, W2 are non-basic. Let me put up a problem for you. So the Y1 column, so your B matrix is going to be the Y1 column and the Y2 column, right? So the Y1 column is 1, -1, okay? And the Y2 column is -1, -3. So you can see the problem, the linear program described on the screen, and this is a y1 and y2 column. How do you compute B inverse? So if you have a matrix A, B, C, D, B inverse is Did I do that right? Okay. So let's apply the same principle. So B inverse is going to be times, so the determinant is -3 minus 1. So it's -4. Okay? So it's going to be 1 over 4 with a minus sign. So the point is B inverse is going to be 3 over 4 minus 1 over 4 minus 1 over 4 minus 1 over 4. So that's your B inverse. Let's actually compute this vector. Okay? So what is B inverse times B? So B inverse B is 3 over 4 is 40 times -2, -3. Right? That is the B vector. This is going to give you so you end up with -3 over 4 and 5 over 4. So if I look at the dictionary and look at just the right-hand side, just the constant coefficients, I should see, if I did that right, I should see -3 over 4 for the y1 and 5 over 4 for the y2. Okay? You can see -3 over 4 for the y1 and 5 over 4 for the y2. Let me just do that computation as well so you see it explicitly once. So if you do B inverse n xn, let me do that here. B inverse n xn is going to be 3 over 4, -1 over 4. N is going to be y3, w1, w2. Okay. Go back to that. So the y3 column is going to be -1, 0. w1 is going to be 1, 0, 0, 1. And xn is going to be y3, w1, w2. So this is 2 by 2, this is 2 by 3, this is 3 by 1. You're going to end up with a 2 by 1. So let's see what happens. Then you multiply these two things, you get. Actually, let's multiply these two so that you can simplify it. So if you multiply these two, you get -y3 plus W1. Okay. And then here you get just W2. Okay? And you get 3 over 4 times this. So you have 3 over 4 times 3 plus 3 over 4 W1 minus 1 over 4 W2. Okay. So that's the first row times this column. This is going to be the second row times the column. You get 1 over 4 Y3 minus 1 over 4 W1 minus 1 over 4 2. Okay? So, again, I think I'm going to put this computation down in the notes so you will have it. So, right now, just recognize that you get a vector with 2 entries. The first corresponds to Y1 and the second corresponds to Y2. So if I computed this and this, and if I write down the equation, what I end up with is the following. So Y1 must equal negative 3/4 minus this quantity. Similarly, Y2 must equal 5 over 4 minus this quantity. Okay. And let me just show you hopefully they're okay. Okay. So you have Y1 equals negative 3/4 plus 3Y3 over 4 minus 3W1 over 4 plus W2 over 4. Similarly, Y2 equals 5/4 minus Y3 over 4 plus W1 over 4 plus W2 over 4. So you get exactly the dictionary that we found. You can compute it with a knowledge of just the B matrix, specifically B inverse. So if you're given a B, you can compute B inverse, you can write down the dictionary, just such a simple computation. The same argument would apply to the last row. Let me quickly just write down the expression. I'm not going to evaluate it, and that will be the basis for the proof of strong duality in the next lecture. So the last row is just Z equals CB XB plus CN XN. Okay? Now this violates the dictionary format because XB is not allowed to appear here. Everything should be in terms of XN. So we use this expression for XB and substitute it here. We get CB B inverse B minus CB B inverse N XN plus Cn XN, okay, which is CB B inverse B minus CB B inverse N. So this is going to be the last row of the dictionary. We've already computed B inverse N XN, so you can actually easily compute the last row and verify that it corresponds to what we have over there. Now the interesting thing in all of this is the following. So suppose B is an optimal basis. Okay, so suppose I give you the optimal set of basic variables. Then this is going to be the objective value. It's going to be CB B inverse B. Okay? This is the objective value associated with the current solution. Current solution is given by B inverse B. CBXB is going to be the objective value. Okay? Then these coefficients are going to be the coefficients of non-basic variables. And if you know that that this is an optimal basis, then you know that this quantity inside the parenthesis is positive, so that you have a net negative coefficient everywhere. So what we are going to do is assert that CBB inverse, this is the dual solution. Okay? So we are going to assert that this quantity gives you the dual solution, and we're going to prove that in the next lecture. But here's a clue: if your non-basic variables, let me not say anything more. So we are going to show that this is going to be the dual optimal solution, and this will satisfy dual feasibility, and its objective value will be the same. So we'll pick these up next lecture. I'll put some of these in the notes and post it. No, not at all. Do whatever. Yeah, I think it's